This is what? What is this relation? What is this relation? What's this relation? Why V should be 0? This is the good condition. Okay? I have this guy, this is already 2 V3/4. So let's derive an expression for this guy and just come back to substitute. Any question? If you have any question, please stop me.
Can you tell me again what the NC is? Because I didn't count.
What is, I'm sorry?
What is NC?
What is unsteady?
V theta NC.
V theta, oh yeah. V theta, you know V theta, tangential velocity.
Yeah.
NC stands for non-circulatory.
Non-circulatory.
We said Theodorsen at the beginning divided the problem into non-circulatory and circulatory.
Okay.
Non-circulatory, we don't have any vortices.
Oh,
Here we're adding another part for the problem, we're adding vortices.
okay.
So we did this last lecture, and we already derived an expression for V theta, the non-circulatory.
Okay.
I have a question. Why is it 0 again? Because of the Kotta condition?
Yes, because for this guy to be finite at the trailing edge, which means that theta equals 0, the denominator is already 0. So the only thing, the least, or the necessary condition for this whole thing to be finite is the numerator to be 0 as well, so that you have 0 over 0. Because if you have any number over 0, this is infinite. But if you have 0 over 0, this is not determined yet. You can use L'Hopital to get a number, hopefully. So a necessary condition is that this guy has to be 0 also,
Okay.
right? The non-circulatory component alone is not 0. So we will add a circulatory component such that the total is 0. Okay? This derivation is not hard. Actually, it's very simple. You're supposed to do it. Maybe next time I will ask for the same problem because it comes from the same problem that gave you D. It's the exact same thing. So let's just do some training together. So I have your cylinder, I have a vortex here, the x-axis, the distance x, large x, large y, we are in the zeta domain, the cylinder domain. I have a vortex here, this is gamma, this is again gamma, and this distance is d, where we already know d in terms of the cylinder radius. So take a point here at an angle theta and get the tangential velocity. Let's do that. So how do you do that? Construct your complex potential. So the complex potential for a vortex, it's gamma over 2 pi I ln zeta. But this is if the vortex at the origin. If it's not at the origin, you simply subtract its location. Its location is at x. And then the other vortex is negative, the same thing, but instead of x we have d, right? So here ln zeta minus d. Any question about this formula, please? If you have any questions, stop me. Any question? Because you will do this in your, I mean you did it for your homework, but you will do it in the midterm for sure. Any question? Now I get the complex potential, the complex velocity, just differentiate this with respect to the argument. So this is gamma over 2 pi I, 1 over zeta minus x, 1 over zeta minus d. So this is gamma over 2 pi I. And we have here x minus d divided by zeta squared minus zeta x plus d plus xd, where we know that d is b squared over 4x. So I'm going to substitute it in the next statement. And also I don't need w bar at any zeta, but on the cylinder with zeta is b over 2 e to the I theta. Okay? So this is gamma over 2 pi I, x minus b squared over 4x, zeta squared b squared over 4 e to I theta, b over 2 e I theta, x plus b squared over 4x plus x times b squared over 4x, so you have b squared over 4. And this is the complex velocity. If you want the real and imaginary, if you want the x component, y component, get the real and imaginary. But if you want the radial and tangential, you need to create e to the negative I theta, right? And take the coefficient of that. So I'll multiply up by this black quantity and down. So this will go away, this will go away, and here I will have e negative I theta. And you can see this term, e I theta, e negative I theta, so the addition will give you 2 cosine. So this is gamma over 2 pi. The I will go up with negative I. And we have x minus b squared over 4x divided by b squared over 4, 2 cosine theta, this is these two terms, minus the rest, which is b over 2, x plus b squared over 4x. And this is multiplied e to the negative I theta above. So the real part is the radial velocity, which is supposed to be what? Supposed to be what, the radial velocity?
0.
0, exactly. This is how we determine d. If you didn't substitute for d, you will have d remaining, and if you get the radial and equal to 0, you will get that equation for d, which you're supposed to do in your homework too. Okay? And the imaginary part, the negative, the imaginary part is v theta. So here is v theta is gamma over 2 pi. This is taken care of, and I have this guy. I will multiply up and down by x, and maybe take b over 2 down. So this is b. So overall, here x squared minus b squared over 4. Down here is x squared plus b squared over 4 minus bx cosine theta. So we're done. It was not that hard. We got the tangential velocity at any theta, due to a vortex gamma located at x and its image. Okay?
Professor, why did we not include the complex potential of the cylinder?
The complex potential of the
cylinder in the very beginning? We just have these two sources.
So you could do that. I mean, this already dictated d. The complex potential of the cylinder tells you that the cylinder is a streamline. So it's as if this will give you d. So it's as if we already accounted for it.
I think we need to add the complex potential of the cylinder only if there is also a free stream.
Not necessarily. He's correct. I mean, so here's the point. I have a vortex, just a vortex. What's the complex potential? Gamma over 2 pi zeta minus x, right? This guy. Gamma over 2 pi I then zeta minus x, correct? If you want to get the complex potential of this vortex and the cylinder, right? Then you apply the Melton-Thomson circle theorem. But then there is no need to add a vortex inside. So the way that Theodorsen, this is one way of doing it, but you can do it in the other way, is that, okay, I'm going to add a vortex inside, and I will let them together make the cylinder streamline. The main objective of the Melton-Thomson circle theorem is to make the cylinder streamline. So if you can do it other way, it's your choice. Yes, you have a question, I'm sorry?
No, I was just answering it. I think it's either or.
Oh, you said U infinity? No, not necessarily. Whatever flow. Maybe U infinity or any other thing.
Okay.
Yeah. Yes, Joseph?
From the red to the green,